correlation coefficients, which are essentially at the heart of the Berserk tennis ball company problem, are readings of the strength of a linear relationship between any two sets of data. Correlation coefficients, when you're working with them, there's essentially two issues. One is calculating them, because each one is the result of a big long formula, and the other one is interpreting them. Like, what is the result of that big long formula supposed to mean? The Berserk tennis ball company problem only requires you to interpret them. Let's take a look. You are a quality management consultant for the Berserk tennis ball company. Berserk is redesigning its current model of tennis ball, and you are asked to use, QFD analysis. Correlation coefficients are the engine or the heart of QFD analysis. All right, to make suggestions about tennis ball specifications. You survey customers, gather data, crunch numbers, and produce the following correlation matrix. These are all correlation coefficients. Now, which of the following is apparently true? Looking at your correlation matrix, we have to interpret some of these numbers. Okay, with correlation coefficients, remember that they are a single reading or a score on the strength and the direction of any relationship between two sets of data. What we have here, for instance, in part A, is 3 different statements. Each one needs to be tested separately. Each one of them concerns some correlation coefficient or a particular number on this table. So one key to breaking this task down is first simply locating the number that a particular statement is talking about. So let's begin with statement 1. All right, it says customers indicate that tennis balls with thick shells stay bouncy longer. Remember that a correlation study in QFD analysis will be essentially measuring the strength of the relationship between various technical specifications and various customer attributes. That's what QFD analysis is about in particular. The thickness of the shell is a technical specification, and I see it there. This business about staying bouncy is a customer attribute. So first off, in order to test this statement 1 right here, I need to locate the correlation coefficient that's at the intersection essentially of this row and this column. That's the measurement of the strength of the relationship between the thickness of the shell of a tennis ball and whether it stays bouncy or not. And I see that it's 0.994. All right, we remember that when interpreting correlation coefficients, they can range from 1 to -1. Anything close to 1 is an extremely strong positive correlation, meaning that these two separate issues or sets of data look like they kind of like work together in lockstep. Anything near -1 is also a strong relationship, but it's a strong negative correlation, meaning that these two things tend to move in the opposite directions consistently. Now, what we just discovered is that for statement A, the two things that were cited, they do seem to be very strongly related. To finish off our classification of statement A, whether it seems to be supported or not, or I should say statement 1, the first one, we have to check the direction of the relationship, because the only thing we've observed right now is that, oh yeah, good, that does look like there's a very strong relationship. 0.994 some odd is positive, meaning a strong positive relationship. Is that what the customer thinks? Now, how do you test that? Well, let's look. Okay, so customers indicate that tennis balls with thick shells, thick is more, stay bouncy longer, more. These are essentially two positives. That means that they think there's a positive relationship between the two. Yes, that's confirmed. That's exactly what that's indicating. Okay, so right away we know that we want to preserve this one. Customers indicate that tennis balls with thin shells stay bouncy longer. All right, the second statement, now we can go through all those same steps. Locate the correlation coefficient being discussed. Well, wait a minute, that's that same one that we were at before. Yes. Oh, okay, then classify the direction of the relationship that's being specified, if indeed one is, and there is. It says thin shells, less, 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 stay bouncy longer, more, more, more. That would be negative correlation. Oh, check the correlation coefficient. It's not negative. Oh, that's not supported. Yeah, I just went through all those same steps in order to classify the second statement. We can cross it out. That's not supported. The ironic thing is that I didn't really need to if I had noticed that statement 1 and statement 2 are mutually exclusive. One of them, if one of them's true, the other one's got to be false, right? They kind of exclude each other. They can't both be true simultaneously. And since we'd already worked on one and knew it was true, if I had noticed that, I could have just X'd out 2. It'd have to be false, right? Because you can't have it both ways. All right, now, the third one, though, we are going to have to work on regardless. Customers indicate that tennis balls with thin shells stay clean. Okay, thin is less, 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 right? Stay clean is good, more, more, more. So they're thinking that there's more of a negative correlation, but we have to locate the actual score. Okay, so we're still talking about thickness of the shell, right? We're saying when it's less, 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 they stay clean. Stay clean, the customer attribute, that's this column. So the number that we should be looking at is that negative 0.17. And you might look at that and say, oh yeah, well you said that that's a a negative relationship that they're talking about. Thin shells, stay clean. But that's like a really weak number. It's negative, but we also have to remember that if a correlation coefficient, when you calculate it, comes out like around 0, which a negative 0.17 is not too terribly far from 0, that's not like really exciting. What that's indicating is that we're not detecting a at least linear relationship. Oh, which means that, no, I'm sorry, at least our correlation matrix here, and that number in particular, it doesn't support that third statement. So we have discovered for this part that 1 is the only statement that's definitively supported by our correlation study. Let's look at the second question. Which of the following is apparently true looking at your correlation matrix? Okay, so this is kind of a repeat type of exercise. It's good practice interpreting correlation coefficients. Statement 1. How easy a tennis ball is to see. That is a customer attribute. An opinion is related to how much latex is used in creating the shell. Now notice it just says is related to. It doesn't indicate particularly a positive or a negative relationship. Oh, all right. So we would just be looking for a strong correlation. Let's actually locate the number we're supposed to be looking at. Easy to see. Oh, easy to see is this first column right here. Okay, easy to see. And then how much latex is used in the shell? That's that bottom row. This column, bottom row, 0.236801. That's just not a very impressive correlation. I'd like to see something like 0.7, 0.8, 0.9. It's still kind of meandering around 0. I'd say, no, I don't see definitive evidence of that. And it would sort of make sense because it's very hard to see the shell in a tennis ball, so how would it be related to its appearance anyway? Anyway, how easy a tennis ball to see is related to the depth of its nap. Okay, so we're still talking about that customer attribute. Is it easy to see? Is there any strong relationship between that and this is a technical attribute, the depth of the nap? Okay, easy to see is this column. Depth of the nap is the second row. And I see negative 0.984 some odd. That's a very close to negative 1. That is a very strong correlation. Yes, our correlation study here is indicating that there's apparently a relationship between the depth of the nap, that's that fuzzy covering on a tennis ball, and whether the customer perceives that it's easy to see or not. Now you might say, yes, but it's a negative correlation, right? Is that asking for a negative correlation? Well, statement 2 doesn't really indicate positive or negative. It's just asking if there's a relation. So in that case, when you're interpreting the correlation coefficient, it's just as good if it's near 1 or near negative 1. At any rate, 2 is a keeper. Let's look at 3. Customers think the current model of Berserk tennis balls bounces funny. Bounces funny. Well, doesn't bounce funny is a column here, but this particular question here, the statement here, that's a distractor. Maybe customers do think that Berserk's current tennis ball bounces funny. I don't know. You couldn't tell from our correlation study. Okay, the only thing that we can comment on from our correlation matrix is any specific relationship between these certain technical specifications and these certain customer attributes. Anything else, such as for this particular tennis ball, if they think like one of the attributes is or is not true, you can't read that from this data. So it's just not supported. Oh, so the only thing that we can keep here in this case is 2. Let's see, what's next? Oh, the next part of the problem explains that the nap is the fuzzy covering on a tennis ball. Berserk is considering changing the nap on its tennis balls. What suggestions would you have based on your correlation analysis? This sounds like it's a different kind of question, but it's not. We have 3 statements, 3 proposed suggestions that you might make from, still the same exercise. You have to evaluate the statement, look up the appropriate correlation coefficient, and just what we were doing last time, determine if the statement is inappropriate. Okay, now let's go on to the statements. If Berserk makes the nap deeper, more depth of nap, a fuzzier tennis ball, customers will probably complain that the new model of tennis ball doesn't stay clean long. So this is a question about the relationship of the depth of the nap with the customer's perception of whether a tennis ball stays clean. We can relate this back to our original matrix, because our study did include depth of the nap, and there is one number here, depth of the nap, that does concern its relationship to their opinion of tennis balls staying clean or not, right? So that would be right there. It says negative 0.97 some odd numbers. Negative 0.97, that is a very strong negative correlation. That means that when one got a high score, the other got a low score. So when one got a high score for depth of the nap, meaning it was fuzzier, that same tennis ball got a low score for this issue about whether it stays clean or not. That is a negative correlation. That's exactly what the statement said. Yeah, actually that number is a warning if you're thinking about revising the design of Berserk's particular tennis balls, that this is potentially true. If they do make the nap deeper, it's likely they'll get more complaints about it staying clean, because those things are negatively correlated. So we're going to want to keep that one. What about this one? If Berserk increases the amount of nylon in the nap, so we have to be alert here. We have changed the technical specification. Customers will probably complain that the new model of Berserk tennis ball doesn't stay clean as long. So this looks like it's another proposed negative correlation, because if they increase the amount of nylon in the nap, that's more, complaints about staying clean, lower scores, less, moving in the opposite direction. In order to confirm that, what we need to do is locate that particular correlation coefficient and then check if it is strong and negative. Okay, percent nylon in the nap stays clean. That's this one right here. I see 0.26211. That's kind of unimpressive. Doesn't support that there's any linear relationship at all. Okay, we're gonna have to discard that one. This particular study, it doesn't support that statement. Okay, third one. If berserk makes the nap deeper or fuzzier, okay, so that's what we were looking at originally, customers will probably complain that the new tennis ball is more difficult to see. All right, so if they make it deeper, fuzzier, that's plus, more. Customers will complain more difficult to see, less, so that's negative correlation. Did we get a distinct negative correlation between depth of nap, right, and easy to see? Oh yeah, we've been here before for another question. That was that negative 0.98. That is a strong negative correlation. That is definitely supported. If they do that, they probably will get more complaints. Those two things do seem to be related in a opposite fashion. So we would want to forward 1 and 3 here as suggestions that are essentially supported by our study. Now, the last part of this problem. Assume that customers considered the first 3 attributes to be equally important. Okay, and consider one to be 3 times as important as the last attribute stays clean. Oh, excuse me, and consider each one to be 3 times as important as stays clean. Okay. Furthermore, no known synergies exist among any of the technical specifications. Okay. Sketch a complete QFD house of quality diagram. That's why we needed to be told these things, because they belong on the diagram. Organizing all of Berserk's product design information. Okay, a QFD house of quality diagram features the results of a correlation study, although it generally does not display any numbers, such as what we have here at the beginning of the problem, because the finished house of quality diagram generally only displays indications of the really strong correlations, because those are the relationships that we then become interested as we ask questions about how to improve a product. Anyway, to draw the diagram, the first thing you want to do is draw the framework. Why is it called a house of quality diagram? Because it winds up being shaped like a house. To start drawing the house shape, we remember that of the table in the interior of the diagram, traditionally the rows are the customer attributes, so be careful with this problem. In a house of quality diagram, the rows are the customer attributes, so we would want to list, let me think, easy to see, and then I'm going to need a straight edge. I don't trust myself. That's one row. And then doesn't bounce funny. That's going to be another row in the house. Then stays bouncy. Okay, that's good. And then stays clean. That'll be the bottom row in the house. Notice that in this problem, these are the columns in our correlation matrix. But traditionally in drawing the house of quality, it's the customer attributes that are the rows. The technical specifications become the columns, so I'm going to have to be careful here. First off, I want to put in a column. Why don't I draw a cap on easy to see, because that'll be the top of the square part of the house. And I want to draw a column and leave it empty. I can make it fairly skinny. What is that for? This is going to store the weights of relative importance. Here's where we're going to store numerical indications of, relatively speaking, how important do the customers think easy to see is versus stays clean versus stays bouncy. That is stored right here next to the attributes. Then come the technical specifications. So let me check back here. We have 1, 2, 3, 4, 5. I need to draw 5 columns. 5 columns. Let's put the edge of the house here. So I want to divide this up into 5. Yeah, there we go. More like that. First column, second column, third column, fourth column. Oh, and then I want to label the columns. Of course, the technical specifications had fairly long names. So why don't we just agree in my work that thickness of shell, we'll label thickness. Oops, got kind of muddy. Depth of nap, just write depth. Density of nap, we'll just write density. Percent nylon in the nap, nylon, and percent latex in the shell, latex. That way, I can just write, let's see, thickness, thickness, and then depth for depth of the nap, and then density for density of the nap, and then nylon, 4% nylon in the nap, and then latex, 4% latex in the shell. All right, now we're still in the first step. The first step of developing a QFD house of quality is to simply draw the framework of the house. Now, why is it called a house? Because it's not very house-shaped right now. Oh, because there's one last part to just this framework, and that's that we need a top to the house. The top to the house would be where we would store indication of any relationship or synergy between the technical specifications. For instance, if the thickness of the shell was strongly positively correlated with the percent latex used in the shell, I mean this one and this one, you'd put a symbol up here indicating that. That's where we get essentially the rooftop of the house. Now you're thinking, this is messy. You drew all over that paragraph. Yes, but it doesn't bother me because the synergy matrix between the technical specifications for this particular problem, Berserk Tennis Ball Company, this is empty. I know I don't have to bother with it. I didn't even really have to draw it that well. It's going to be completely empty because they said furthermore no known synergies exist among the technical specifications. Yay! That means this top part is finished. This top part's finished. The framework is finished. The only thing that we need to do is fill in the weights and then literally fill in, this is called the relationship matrix. Okay, so first the weights. We were told something about weights. What were we told? Okay, the first 3 attributes, easy to see, doesn't bounce funny, and stays bouncy, are considered to be equally important. And each one of these is considered to be 3 times as important as the last attribute, stays clean. Now, how am I going to express that here? Okay, generally, the way that we express this is by assigning scores. And the most typical way to assign those scores to express this business about, oh, these 3 things are equally important and they're each 3 times as important as that one's like not so important. The way that we do that is we usually take a budget of points, like 100 points, and we divide it among them according to who's more important and who's less important. Now, how are we going to do that? Here's what I recommend. This is just a side methodology for weighting schemes. You could probably figure out what those weights should be to add up to 100 to reflect that statement that's in the paragraph just by trial and error, but let me show you a trick. First off, what you do is you look at the original statement and you look for the least important attribute. Okay, the least important attribute would be this business about stays clean because it says that everything else is 3 times as important as that. Okay, tentatively assign that a 1. This is just like scratch work. It's the least important one. All right, now ask yourself, relative to the least important one, how important are the others? Well, each one is 3 times as important. That means that I tentatively assign a 3, or 1 times 3, to stays bouncy, 3, and 3. And this would actually work as a weighting scheme if I was okay with dividing up by a budget of 10 points. But traditionally, it's a budget of 100 points. But this is not that hard then to modify, because first off, I just add them up. They do add up to 10. They happen to add up to 10. So what I say is, okay, 100 is the original budget of points. 100 times 3/10, or 3/10 of 100. Or 30% of 100 is 30. 30% of 100, or 3/10 of 100, is 30. 3/10 of 100 is 30. 1/10 of 100 is 10. The only thing I did there is I translated the sort of raw scale that I teased out here into an official 100-point scale. Okay, first, this is just a raw scale. Give the least important thing a value of 1, and then weight everything else relative to what it is compared to the least important thing. Whatever that adds up to, essentially make that the denominator. 3/10, 3/10, 3/10, 1/10, and multiply that times whatever your budget is, like typically 100 points. Okay, now we have, out of 100 points, a situation where these are equally important. They have the same score. And that score is 3 times stays clean, because that was the minor thing, that everything else was 3 times as important as. Okay, fine. Now, to finish this, we have to indicate where the strong relationships are. Where the strong relationships are according to the original correlation study, which we have, right? We've been working with here. Okay, now that does imply that we come up with a scale. A typical scale is that there will be a symbol for a very strong correlation, and there'll be a symbol for simply a strong correlation, a notable correlation, but not necessarily very strong. Now, how you classify them, right, that can vary. What I did in my notes is a particularly common scale, where if we see anything 0.9 or above, or negative 0.9 or below, we say, ooh, very strong positive correlation versus very strong negative correlation. And if we see something that's at least like above 0.6, but it's not quite to 0.9, we say that's notable, that's strong. Now, what we do need is we need a symbol for very strong positive, a symbol for strong positive, but not very strong. We need a symbol for strong negative, notable, and then a symbol for very strong negative correlation. Once we agree on these symbols, the only thing that we're going to do is take these original numbers and just encode them on this table. So, for this problem, why don't we let a solid dot be strong positive? So I want to put a solid dot everywhere there was originally a correlation coefficient 0.9 or above. All right, where did I originally have correlation coefficients? 0.9, positive 0.9. Oh, there's one. Doesn't bounce funny, and thickness of the shell. Now here's where we do have to be careful. I want to place then in the finished diagram, it's kind of like a summary, just a solid dot to mean we found a very strong positive correlation. But doesn't bounce funny is a row here, and thickness of the shell is a column. We just have to be careful we put it in the right place. Yes, there was here definitely a strong positive correlation. Where's another one? Oh, I see right next door to it in the original matrix, thickness of the shell and stays bouncy. I want to locate that same location here. Thickness of the shell here is a column, stays bouncy is the row below, that's where that's where that would go. And then if I scan about for positive numbers, I don't see anything else that is greater than, or 0.9 or greater. I do see some notable ones. See how there's one here, density of the nap and doesn't bounce funny, that is 0.7 and also stays bouncy. Oh, we need a symbol for just a notable, but not quite 0.9 positive correlation. Why don't we use a hollow dot so they'll be related? Okay, actually, so where was that? Density of the nap doesn't bounce funnies here, stays bouncy is here. There is also another notable one for stays bouncy and percent nylon in the shell, so I would put that here. Now, those are positive correlations. Negative correlations are equally important. Let's use an X with a box around it to be strong negative. And then we'll just use a plain old X to indicate negative. So what we would be looking for here is first strong negative. We would be looking for negative 0.9 or lower, and yes, depth of the nap easy to see. There is such a reading. I have to locate that here. Depth of the nap easy to see is right there. There is another one very strong for stays clee and depth of the nap. And there are two other strong correlations concerning percent latex in the shell and the bounce factors. So they're over here. If you scan about on this matrix, I did leave a provision. I said if we find anything between negative 0.6 but not quite negative 0.9, we should encode that as notable negative, but they're actually on this matrix. There isn't any correlation coefficient of that description. So finally, that is the finished QFD House of Quality diagram for the Berserk Tennis Ball Company.